Welcome back to our series on relays and relay logic. In this final module, we'll connect the fundamental concepts of relay logic to PLC ladder logic. We'll also review common industrial applications for relays and why they remain important today. Relay applications are extensive, especially when solid-state relays are included. In this video, we'll focus on 5 practical applications, ways relays connect machines, systems, and technologies. 1. Voltage control and management. 2. Interposing. 3. Memory and latching. 4. Interlocking. And 5. Technology interfacing.
Different systems can have different voltage requirements, and these are not interchangeable. You cannot connect a 120-volt light directly to a 600-volt circuit. However, industry often needs a 120-volt control circuit to operate equipment supplied by 600 volts.
A relay can provide that control interface. The 120-volt control circuit energizes the relay coil, while the relay's isolated contacts switch the separate 600-volt load circuit. The two circuits remain electrically separate. When selecting a relay, confirm that the coil matches the control voltage and that the contacts are rated for the load voltage, current, duty, and required number of contacts.
This is a representation of a 10-amp ice cube relay. The 10A marking identifies its maximum contact current rating. The 240/250 VAC and 28 VDC markings are maximum contact switching voltage ratings. The coil is rated separately, in this case 24 VDC.
However, these values do not mean the relay is suitable for every type of load at those limits. Always check the manufacturer's specifications for the proper application and the intended load and duty.
Notice there are 2 pairs of contacts, each with their own common connection point. You can see on the bottom, these contacts are electrically isolated from each other. Putting it all together, you can have one voltage supplying the coil, another source voltage or sign on one set of contacts, and if need be a third voltage or signal source for the other pair. In absolute terms, that's up to 4 outputs controlled by one relay.
Let's go over them. So first of all, we connect the relay's coil to 24 VDC. It should be recorded on the 24 VDC control print. The 8 and 7 indicate the relay screws the relay coil is connected to.
Right. We can now use one set of dry contacts as a switch for the small 240 VAC motorized vent. The 240 VAC supply is connected to the relay's common terminal, terminal 5. The vent motor is connected to the normally open contact at terminal 3, while the 240V yellow pilot light is connected to the normally closed contact at terminal 1. When the relay is energized, the normally open contact closes and energizes the vent motor. When the relay is de-energized, the normally closed contact returns to its normal state and illuminates the pilot light, indicating that the vent motor is off. The second set of relay contacts is wired to the PLC input circuit in the same way. The PLC's 24 VDC supply is connected to common terminal 5. Terminal 3 is wired to one PLC input, indicating vent active, and terminal 1 is wired to another input, indicating vent inactive.
I should add a caution. This example demonstrates the principle, but the exact wiring must match the PLC input type, its sourcing or sinking arrangement, the approved design, and applicable electrical requirements. In practice, not every installation will permit or need this arrangement. The key point is that one relay can use isolated contacts to coordinate more than one voltage system and report an operation to the PLC.
Any time this year. I can't stand here all day.
Hey, I'm busy over here.
Now let's take a look at interposing relays. Interposing relays is a method using relays from different systems to work together. Image if you had a robot that loaded a conveyor. It would need to know when the conveyor was ready to receive some material. At the same time, You may not want the conveyor to run unless the loading robot had put the material on the conveyor. The conveyor and the robot have different electrical systems and need an intermediary to pass along some data. Enter the interposing relays, otherwise known as intermediary relays.
Similar to the voltage control example, these machines are controlled from different electrical panels. We cannot simply connect a switch in one panel directly to the control circuit in the other. Instead, the two systems need a deliberate, compatible interface to exchange their ready and clear signals. An interposing relay can provide that interface while keeping the two control systems electrically isolated.
I'll let you know when I'm clear.
I'll let you know when I had something for you.
Since both are on different electrical panels, you can't just turn on a switch in one and have the other receive it. Even with PLCs, you can't use one PLC's output wired to another's input. It's unsafe and could damage both PLCs, or in this case, machines. So here we put the dry contact and coils to work. The conveyor now has two interposing relays. It will receive 2 bits of information from the robot. 1 ready with a part and 2 clear of conveyor. The conveyor will send out 2 bits of information to the robot. 1 clear to receive and 2 conveyor run.
Each machine has their own set of relays that they will be controlling. So here we wire the inputs to be used by each side through the dry contacts of the other side. Purple wires show the conveyors, requested inputs, and orange for the robot's requested inputs. Both relays all require a common wire to complete the dry contacts circuit, shown here as a red or burgundy dashed line. These will be carrying the 24 VDC signal voltage for each side.
When the robot energizes its clear relay and leaves its ready with a part relay de-energized, the conveyor sees that the robot is clear and has no part ready to transfer. The conveyor's relay logic then permits the M1 conveyor motor to run. In this example, the logic at the robot controller is nearly identical. It uses the conveyor's status signals to determine when it is permitted to present a part. If the machines need to exchange additional discrete information, additional interposing relays and PLC input/output points can be added.
Now let's look at how relays can store data and hold a contact state on. Here is a simple latching or seal-in circuit. When CSR is active and limit switch LS1 closes, relay CR2 energizes. CR2, normally open auxiliary contact, then closes in parallel with LS1, keeping CR2 energized after the limit switch returns to its normal state. CR2 remains energized until CSR is turned off. Why latch a limit switch signal? A limit switch may be made only briefly, and another control device may not detect that short transition. This circuit captures the event and holds it long enough for the rest of the control system to respond. In effect, CR2 indicates LS1 was made. This is temporary memory. If control power is removed, CR2 drops out and the stored state is lost.
There is another reason to latch a limit switch signal: mechanical bounce. This wire whisker limit switch uses a long, flexible actuator to detect an object while allowing the switch body to be mounted out of harm's way. After the object passes, the whisker can overshoot and oscillate as it returns to its normal position. That motion can operate the switch more than once, creating several brief on and off signals from a single object. This can cause a real problem, especially if the switch is used for counting. The latching circuit captures the first valid signal and ignores any additional bounce until it is reset.
One solution is to latch CR2. Later in the logic, a normally open CR2 contact indicates that LS1 has already operated. If LS1 operates again, while CR2 remains energized, the circuit can energize CR3 as a debounce or double count relay. CR3 can then enunciate a problem or be used in the logic to prevent a second count from LS1.
Speaking of solutions, reversing motor starters have a hazard serious enough to require both mechanical and electrical interlocking. A forward reversing starter uses 2 contactors, one for forward rotation and one for reverse rotation. If both contactors close at the same time, the reversed phase connections can create a phase-to-phase fault that can severely damage the starter, motor, conductors, and protective devices. Reversing starters normally include a mechanical interlock that prevents one contactor from closing while the other is closed. The control logic must also provide an electrical interlock, preventing the forward and reverse coils from being energized at the same time. Together, these provide redundancy against a serious fault.
If the control circuit is not designed correctly, pressing the forward and reverse push buttons at the same time can command both contactors to energize. Because contactors and auxiliary contacts do not operate at exactly the same speed, one may pull in first, or the control circuit may chatter or behave unpredictably. That is precisely why both electrical and mechanical interlocking are required. Without them, the result could be very bad.
Now let's take a look at another use for relays within the modern era. I once received the wrong type of proximity switch from a supplier. These were NPN or syncing sensors, while the PLC inputs for this machine expected a positive or sourcing signal. On their own, the sensors and PLC inputs were not compatible. Rather than replacing the sensors immediately, we used each proximity switch to energize an interposing relay. The relay's dry contacts then applied the PLC's own positive input signal to the correct PLC input. The two relays provided a simple interface between the NPN proximity switches and the PLC inputs, solving the compatibility problem. You are looking at a model I built to demonstrate the principle. The metal-covered block triggers the proximity switch. Once triggered, the power turns on a relay, which has an input running through a set of normally open dry contacts. When the relay is energized, the contacts close, completing a wiring circuit to a PLC's input terminal.
Let's take a moment and review what this series has been all about by going over some of the pros and cons of relays and relay logic. Starting with some of the reasons they are still in use. 1. They effective direct wired control for many small machines and processes. 2. Relay logic diagrams clearly represents the machine's logical sequence and provides guidance as to the nature of the devices in use. And some also provide the intended change condition like C. O. Are close on Rise 3, it is still widely understood by electricians and engineers, and uses familiar symbols in their shelf state for relay logic diagram, tend to be designed for order of operation, and have cross-reference notation, quick lookup during troubleshooting.
I guess that makes me the naysayer. Let me begin by qualifying that relay and relay logic still are vital to any automation system. Having said that, here are a few cons. 1. Installation and maintenance costs rise as systems become more complex. 2. Relay logic relies on accurate, up-to-date drawings. 3. Relay logic troubleshooting can be time-consuming, especially after undocumented changes. 4. Relay contacts must be traced and may appear on multiple pages. 5. Electromechanical relays will wear out over time. 6. Changes typically require physical rewiring, and changes may be difficult to integrate. 7. Many changes are not recorded, and you end up with a minefield created by Finkel.
Our next series of videos will focus on PLCs and PLC ladder logic. Beginning with a brief history and overview, all the way through program a micro 850 PLC and using connected components workbench. Again, thank you for watching and leave any questions in the comments.